Morning, good afternoon, and good evening. And thanks for the opportunity to come talk about some of the work that's been going on at Corteva. So my name is Geoff Graham. I lead the breeding team at Corteva. And today I'm going to talk about a little bit of the innovations that have gone on over the last 100 or so years and some of the things that we expect are going to continue to drive that innovation as we go forward. So this is basically the outline. I'm going to talk a little bit about the last 100 years and actually the phenomenal response that we've gotten from selection. And then talk about, how executing on the fundamentals have really driven a lot of this work. And what you'll see is that although we have new ways of doing some of the fundamentals will still be key to our product development future. One of the really neat things about the work that we've been able to do is that we've really shown that you can just leverage these technologies going across crops and across regions to drive strong response to selection. So these technologies really can be used in almost anywhere you choose to use them. And I think when I finish up, just a quick editorial about, I think, some of our future problems and the application of these technologies and how we also have to fold in new crop diversity to build new cropping systems to go on. So for those of you who are unaware about corn, corn really started high intensity breeding probably around the 1920s, and that's when the Pioneer Company actually was founded or started pretty much with the first inbreds way back in 1920. And what you can see is just the response from selection as we started moving from open pollinated material to double cross hybrids to single cross hybrids. And these are the lines across the bottoms here. And you can just see this slope. And one of the things that people always ask me is, where do I think yields will stop? And we've been asked that question a lot. And all I know is that if I look in our pipeline, the material that I see today is yielding more than the material that we've already commercialized. And I just don't see an end for this continual improvement. And it's just an amazing, amazing feature about selection. And one way to think about that is that we actually also plotted on this slope or on this graph what the National Corn Growers Contest, this is the non-irrigated class to mimic what we're doing. But what we see is that, with right management practices, that increase in yield is just continuing to skyrocket. And we really see it moving forward. And in fact, if you take the overall winner of the National Yield Contest, that result was a little over 610 bushels. So just a phenomenal result when you think about it, from where we started back in the 1920s with about 25 bushels per acre. So just an amazing response to selection. And one way to put that into context is just to think about the amount of yield that's actually, or the amount of land that's actually been saved by actually driving this going forward. So if you look at the acres, what would be planted in 2017, these are the corn acres. Darker green is more concentrated corn growing. And these would be the virtual 1926 acres, which basically says how much land would we actually require to use today if we hadn't started on this journey back in 1920. And so I think when you see that, this density of green about how many acres, and in fact, 1 out of every 3 acres would have to be planted to corn in the lower 48 states to get the same level of production that we do in 2017 by the acres above. So not only has this, been a phenomenal agricultural story, I think it's a phenomenal human story. And just the amount of sustainability that's actually driven into our planet. And that doesn't take into account other improvements that we've done in soybeans or wheat or any other commodity crop that's gone out there. So selection is, I think, a very, very, very powerful tool. And we need to think about it as a tool and to help solve our future problems. So one of the neat things about being at a seed company like Pioneer is that we've been around for a while. So the company was started in 1920, so it was actually founded in 1926, but it basically means that we have access to all the seeds, the open pollinated variety and the inbreds during this entire journey. So we go back and we study it to look and see what kind of things have we actually seen come forward or change over time. And so one way to look at these charts is you can start seeing that this is the decade of release. So this would have been open pollinated varieties. These are our most modern hybrids. And on the left-hand side of the axis, we have a couple of different traits: drought, nitrogen, and high yield. And you can see then just yield is plotted. The two dots just represent different planting densities, with the thought that the older material would have been more accustomed to a lower planting rate. So let's measure it there. And the higher material, or the more recent material, would be planted at a higher density rate. But you can see whether it's drought stress or nitrogen stress or just pure yield play, that over time we have selected for and for increased productivity on an acre basis. And I think that's really an important statement to make, that maybe on a plant basis, there are situations where we're not, but on an overall acre basis, on a community basis, modern day hybrids are so much better than older hybrids in just about any trait, which really goes to show you, I think, that we have been continually selecting for new environmental stresses over this period of time, so that the corn crop is much more resilient than where it used to be. And you can kind of see this in pictures, that and I've just taken a couple here in the top one on the left. You can actually see an old hybrid in the background, and an old hybrid in the foreground, and then in the background an older hybrid. You can see it standing up. The new ones stand up, the old ones fall down. So stock pressure is a clear indication. On the bottom left-hand side, you can see the same sort of thing for root pressure. Older hybrid on the left, newer hybrid on the right. On the upper right, and I think these are key traits when it starts thinking about stability, as you can see the flowering synchrony. So in an older hybrid or an older product, you can see maybe one or two silks come out and emerge while the rest of them are still working their way through it. Versus a modern hybrid that has, all the silks come out and then pollen is dispersed and pollinated. And actually flowering synchrony is one of those things that's critical under stress to make sure that you have a crop. And then finally, it's just under drought. And so again, here's decades of release, 20s up to the 90s. And what this bar on the left-hand side, or which each bar represents, is the number of bushels per inch of water. And you can again see that just over time, we have increased the ability of a corn crop to produce more yield per inch of water. It's become more efficient as we've undergone our selection. So, I think it's an amazing story. And one of the amazing outcomes of this is just the development of our germplasm pool. And this is what our germplasm pool looks like today, with each dot being a different inbred. And we started here in the middle, and we actually started selection. And so really one way to think about what we've done for the last 100 or so years is just a long-term reciprocal recurrent selection program. And if you would think about that, really what we should be doing is driving these two groups apart. And that's exactly what's been going on. So if you look today's modern hybrids are crossed from the dots out on the left-hand side by the dots out on the right-hand side. And really just pushing the divergence of these two crops, or these two heterotic groups, so that when they complement each other, when they come and form a hybrid. And we just continue to see our genetic gain growing and growing just by this divergence. And so one of the important points about this, if you are building if you are building or working on a hybrid crop, such as we're working on the transition of wheat right now and trying to make it into a hybrid crop, and we've been doing rice for a while, starting reciprocal recurrent selection to force these heterotic groups apart is really an important part. The other part is that I think you could probably say that, while there is natural heterosis, I think you actually build heterotic groups. You don't just go out and find them. So when we think about our modern day breeding pipeline and some of the things that we really want to make sure that we're working on, it really comes down to this funnel. And for us to think about, creating, and this is a numbers game. So we want to create as many new genetic combinations as we actually can, and then just have a responsible selection intensity as we go through. And so this is really going to come back to saying, how well can we phenotype so that we can do our selection as we go through this pipeline? The other component is that we just have to recycle this material. And so you want to make sure that you recycle this material when you have a certain level of confidence that the inbreds that by this stage are actually good enough to put back into your pipeline to make these combinations. So if you can do each one of those better or faster or quicker or cheaper or longer, each one of those is going to make your breeding programs faster. And so when we really think about it, we think about the fundamentals of population development. You know, a newer one probably is the cost of genotyping and our capacity to genotype. Phenotyping is key, and you'll see that come through and through. Prediction analytics, experimental design, and then advancement systems. And I won't talk a lot about advancement systems, but I think if you don't have a good manufacturing system to put the final product ahead and to make sure it's commercialized through a pipeline, then you really have some difficulties of being a reliable producer of good products. And I think this is a big challenge in some areas of the world where you really want to make sure that there's rules and things in place that the customer gets the product that they think they're going to go get. So like I said, we do a lot of investment into just building some of these technologies that we've talked about. And, you know, it's really about making them either, you know, widening the funnel, recycling quicker, or going faster in this. And what I thought I'd do now is just talk a little bit about some of these technologies and a little bit of the journey that it went through, and just to show some of the thought that went behind it. The other thing that I think is a strong recognition that we do is that, you know, in terms of a philosophy of product evaluation, we're using more and more genetic information at the early part of this funnel. And one of the reasons is because it's cheaper to genotype than it is to do anything else right now. And then as we go down the funnel, as we get towards the end, we rely more and more on confirm our expected performance based on the actual phenotype measured across years and locations. And so this is another one of those things that shifted quite strongly, probably really strongly over the last 10 years. So this is our population development strategy. This graph is just showing you double haploids being produced at some of our winter nursery sites. And you can see some of those things down below, and I'll get to those in a second. Each one of those dots is a shipment of, I don't know, 100 to 500 double haploids coming out of some of these core sites. And I like to think about this as kind of like an explosion of genetic material coming out and making sure that it's the material that the breeders can use for their product development cycle. So the beginning of the material up here. And in order to do that, we needed to create some environments where we really babied some of the haploid plants to make sure that they produced the right seed in the right volume. And these are some of the infrastructure sites that you go down here. The other thing you can see in the chart where the dots are coming out of is just our different regional production. So as you start seeing Latin America, Hawaii, Asia Pacific, and China, you know, we started producing in all places, which is again just an exportable part about the technology. But this allowed us to really just think about population development in a very, very different way than what we had done before. The second technology I'd like to talk about is just how much we spend on phenotyping. And so, of course, we have planters and we have combines and we put them out in nice yield trial plots that you can see down here. But every once in a while, we have to create new equipment to actually go out and figure out a new trait or a different trait. And this is for brittle snapper, when a storm causes a corn plant to blow over and actually break below the ear. And that's what this machine is here, and the one that you see the video of going through. And what that thing really does is it just, when we were trying to do this with a natural windstorm, it was so variable across a field this big that we got really poor data quality. And so it was really hard to actually make advancement decisions. But once we actually did complete this or did make this machine, what we saw was that the genetics of the trait were actually simpler than what we thought about, and we could drive our heritability up, and then we could start making really good selection for improved performance for our customers' field. So sometimes you have to really spend a lot of time just to generate this machine, and it probably took us 6 years to just think about the development of the concept, which was a wind tunnel, to this machine going out into the field to measure performance for brittle and root lodging and other wind-related events. So, you know, on the left-hand side up here, I forgot to mention that this is just our normal, you know, normal locations about where we characterize, and these are just the different crops that we work with. And over on the right-hand side in the middle was just the same sort of location where we actually started taking drone images. And one of the things I would comment about drones is it's really changed our perspective on how we collect data. And so last year, I think there was about somewhere between 60 and 70 million data points collected. So that would be one individual plot of whatever crop we were measuring, going across crops and across all locations. And the thing that was found that's, I think, really just comes out again and again and again is just how much human error there was in scoring. And so having something that can go fast and quick and cover acres and acres in a fairly quantitative fashion really has removed our error from our system. And so that's allowed our heritability to go up. Once our heritability goes up, you can kind of shape that funnel a little bit better, and you can drive your selection intensities. And so this has been invaluable to us. And I think where that's going now is to just start thinking a little bit of how does satellite imagery and farmers imagery come into that and play, and you can start thinking about some of the different spectrums and cameras that you can actually use to go make crop productivity play or selection. Now, this is a new thing. I think we're continually developing on new traits, but phenotyping. Someone once asked me and said, what would you like to see? And I said, I'd like to measure every single ear in an entire field of corn. And what you're just seeing here is a fisheye lens this is a prototype, a fisheye lens of a camera walking through the field, allowing us to get measurement of every single ear in the field. And the reason why that's valuable is because normally what we see is at the end of a plot, you get a nice developed ear, and in the middle of a plot, you see smaller ears. And that level of stability as you go from the end to the middle, I think, is going to be very predictive of the stability of that product in general. So developing things like this and just continuing to think about new ways to measure will be something that I think we do for a long time. The next thing I wanted to talk about was just genotyping, but more than just genotyping, also talking a little bit about the predictive analytics, and we'll get into that next. But like I said, when I started off in grad school, I mean, this was the limiting thing, is how do you genotype? And so all studies were limited on size because of just the cost of the data point. And what we worked hard on in about from the early 2000s to about 2010 is what sort of new equipment do we actually need to be able to drive our costs down and our sample numbers up. And once we kind of got this thing solved, it really opened up a new way of breeding, and to think, okay, if genotyping is no longer an issue, if genotyping cost is no longer an issue, how would you breed? And this is where, you know, the predictive analytics came into place, and it allowed us to look at certain response to selection things that we were trying to do in a very, very different light. And I'll talk a little bit about that in the next couple of slides, just to show you our confidence in predictive analytics. So what we do every once in a while is, well, more than every once in a while, we run these big breeding experiments just to make sure that we're getting the right data that we need to make sure that we're not making mistakes, because making a mistake is a pretty expensive thing. So I'm going to talk about one of those experiments now, and this was called the Big Bid experiment. But basically, we took about 2,500 double haploid lines, we crossed them to 3 testers, and we tested them across 3 years, so at about 20 locations each year. So lots and lots of data to allow us to look at saying how repeatable, G by Y, G by E, G by L, error rates, and then also just look at our predictive capabilities that were going on. And so I'll just show you a couple of charts out of that study, just to show you the improvements that if you put all these pieces together, the impact that it makes on your performance. So this first chart here is just looking at the correlation of raw data from the exact same entries planted in 2017 across 2018. So these are the means across locations on one tester of all double haploid lines in 17 versus 18. And fairly decent correlation, right? But this is a lot of data. So you know, you can start thinking about subsampling strategies about what you would do. But if you just put in the right experimental design and you take care of error just using phenotypic adjustments, you can see that your correlations improve quite a bit. And so this is just using blobs. And so just setting up your experimental design and your analysis capability gave you quite a significant improvement in that correlation. And it really, as you can see, removed just a lot of noise out of the system. And I think that's one of the key things that we continue to do, is just saying, how do you remove noise out of the system? And the final one is just when we start incorporating marker data and looking at the improvement that we actually see and how tight that actually cluster gets. And to think about that correlation. Now, again, lots of locations, but about looking at that correlation between 2017 and 2018 and the improvement, right? So just staggering how much better we can get if we just use the right analytics to get get an estimate of what the true breeding value of an individual is. So I think pretty powerful just visualization on something so simple. So the next one that I'll talk about actually though is probably where it's you know, pretty powerful to think about the future. And the reason why we value something like Big Bit is because you have so much information over so many years, you really do feel that you're getting to a pretty true value or breeding value of an individual double haploid line. So it serves as a gold standard. And what we wanted to do was just to say, well, what's if we took an external training set, so different genetic material related to Big Bit, and just predicted the Big Bit performance. And this was a work done by a breeder in Windfall, Indiana called Mike Gines, and there's a group of folks out there that's doing this. And you know what it really showed was how good our predictive our abilities are, that if we create the right training sets and we build those up, then our predictive abilities are really quite strong. And so on this biplot, what you see is just basically the correlations between the predicted part. So again, we took this external set, just predicted what that double haploid was going to be, and we correlated it with the observed. And so you can see the traits that we have out on this chart. You can see moisture, yield, plant height, ear height, and test weight. And so this gave us a lot of confidence to just say, hey, look, I think prediction methodology and the systems that we've actually set up will really drive our selection intensities going forward. And I think one of the things that you do actually, if you start including this external training set and develop it appropriately, is some of the variability that years might have. You actually start building that into the model, and that's why some of these phenomenal results actually show up. So in our mind, in our strategy, one of the things that we've done is that we think about our global company, local product development. And so the chart on the left is really just going to showing you where each one of our research centers is located across the world for all different crops that we have out there. And the only crop I don't have listed is alfalfa right now. But I think the most important point that I wanted to get across is that as we've built these technologies, we've built them so that they can be leveraged across all crops. And so today, for example, our millet breeders in India actually have access to the same exact technologies that our North America corn breeders have. And so all this prediction, all the genotype, all the phenotyping work that we've talked about, it's a technology package that really can be applied in all situations. And the thing that I think is most important is actually making sure that you have the right genetic material and the right phenotyping capacity locally to make sure that the prediction capabilities that you want to drive are actually correlated to the environments in the germplasm where you have them and where you're doing product development. And that's fundamental and pretty simple, but it's pretty key to go do. So, when I think back to the 100 years, I think we've actually been developing new cropping system, or certainly been selecting for a cropping system that's more resilient than the one beforehand. And I think it's really important that we recognize it. And the charts that I showed that would go on in terms of moisture or nitrogen or just yield performance on corn, I think is really indicative of that kind of power of selection of what we've actually done. And so for me, there's no doubt about what we've done is that we've, one, increased the genetic potential. We've made that genetic potential, also more sustainable. So we're driving sustainability in that thing. Things like GMOs have done a great job of actually protecting some of the field yields that we have out there. So BTs really do a very, very nice job. And so you can go to places of the world where we don't have BTs, and you can actually see the variability is much higher than in places that we don't. And, I think like some of the new rotations that have actually come through. So corn soybean rotation is I think a great rotation. And one of the new additions, I think, is when you start thinking about the amount of no-till soybeans that go on today. It's just a better cropping system than what we've done. And so as I think about some of the pressing needs of the future, I think it's really going to be critical that we have all our tools available to us. And I think I'll use an example here. So when I mean all our tools available to us, I think of selection, breeding, transgenic technologies, but genome editing. And I think with all the regulatory stuff that's going on around the world, I think it's probably really limited the use or the discovery of that technology into agriculture. And let me be clear, I think as we go forward, we always have to be responsible stewards of the technology. So you should be in a system where there's an approved process to go through to make sure that that technology is managed in a responsible fashion. So clearly support that part. We just need to make sure that some of these technologies are available to make the productivity improvements that we have going forward. So, so I think this is the editorial part, that I think in order to accomplish some of the most pressing needs that we're going to have into the future, we're probably going to have to take and look at new crops that might be more naturally tolerant to some of the extreme conditions that we face. And so, you know, I listed a couple out here on the right, but I think it really becomes important to start thinking about by region, what's our starch, what's our protein, what's our oil crops going to be. And my only point here is that all the tools and technologies that we've actually deployed today really can be used in any of these crops. And I think this is where public-private partnership really has to take over, and figuring out how do we work together to actually move some of these other crops in other regions forward. And I think if we do it wisely, if we do it in a very structured fashion, I think we can make, you know, just great results. And that's why I've always liked this quote by Charles Darwin, that man can select, preserve, and accumulate the variations given to him by the hands of nature, almost in any which way he chooses, and thus he can produce a great result. So I think it's, you know, one of these things that we're going to have to come up here soon is how do we use all the science and technologies and the systems of people that we have around the world to actually start driving some of these product changes that we'll probably need to be successful in the upcoming years and decades as the planet changes. So just to wrap up real quickly, I think, you know, 100 years of selection, obviously a phenomenal success. And really that success has been driven on just the basics, the fundamentals. And it's the fundamentals that we actually are finding new ways to do, but the fundamentals are still the fundamentals of breeding. And so as we've developed these technologies really are leverageable across crops. And I think you can drive, you know, incredible results. But the one thing that I would say that we need to probably start thinking about or doing more of is how do you use those technologies and using that in a crop diversity way to bring that into new production systems to solve some of the world's most pressing needs. So with that, I think I am done, and thanks for the opportunity for the talk today.